In this video, we're going to try to find the relative extrema, or the relative maxes and mins, for this function f of x equals x minus 4x over x plus 1. Now we know relative extrema are likely to happen where the derivative is either 0 or undefined. We call these places critical values. So I'm going to take the derivative of f. But before I do that, let me take a look at f and see if there's any places where this function's not defined, because if I get any critical points at those places, then they're not actually critical points. The critical points have to be in the original domain of the function. So one thing I noticed right off the bat is x is not allowed to be -1, and so let me just keep that in mind as I go forward, because there's going to be an asymptote here at -1. But with that being said, let's differentiate. Derivative of x is 1. And then this guy would require the quotient rule. You would say the bottom times the derivative of the top minus the numerator times the derivative of the denominator all over the denominator squared. Okay, now it turns out you can do a little algebra on your page there, but I think this numerator will simplify to just be a 4. You can check my algebra in that. And so we get 1 minus 4 over x plus quantity squared. And then I'm curious, where is this 0 and where is it undefined? I need to check these two places because that's going to be where my critical values are. So let me start with it set equal to 0 first of all. So if you take this term and add it to the right hand side, you would have 1 equals 4 over the quantity x plus 1 squared. Okay, next we can take this x plus 1 squared and multiply it to the left side, and at the same time I'll go ahead and FOIL it. First outer, inner, last. You'd have x squared plus 2x plus 1, and that's still equal to 4. And then this is a quadratic equation now, so we know how to solve these. We'll move everything to the left hand side so that it's set equal to 0. So I'll subtract 4 from both sides. And then once it's equal to 0, then I'll try to factor it. And this one does factor, so that's good. It would be an x and an x and a plus 3 and a minus 1. And this will tell us what our critical points are. One of the critical points is at -3, and one of the critical points is at 1. And now what are these places? Well, 1 and -3 are x values that will make the derivative be 0. That's what they're doing. So they are critical points. Now if you also look at the derivative, here I'll highlight it in yellow. Here's the derivative. We also need to see, is there anywhere that the derivative is undefined? And there is. At -1 it's undefined. But it turns out we're going to have to not include that in our list because it violates the property of even being in the domain of the original function. So if -1 made the derivative not exist, but -1 was able to be plugged into the original function, we would call it a critical point. But that's not what happened here. So it turns out we have critical points at, let's see, what were they? It was -3 and 1. X equals -3 and x equals 1. So we're going to want to put these on a number line and pick test points, and that'll tell us where our relative extrema are. So we'll do that right now. So we've got -3 right here. We have +1 right here. Now I do understand that -1 is not a critical point per se, but it is somewhat important in the sense that it's showing us where an asymptote is. And you could easily have something change from increasing to decreasing on opposite sides of an asymptote. So I am going to put it on my number line, but I just want to be very clear that this is not a critical point. This is where f is undefined, where these two here are critical points. So let's pick some test points. We'll choose like -4, -2. I'm looking for points in between each of these critical points, or points not in the domain, 0 and 2, let's say. And we're going to take these and we're going to plug them in the derivative function. And then what that's going to do for us is tell us what the slopes are in each of these little sub-intervals here. And I don't even care what the numbers are. The numbers are pretty irrelevant. I primarily care with what the signs are for the derivative. So here's f prime right here. So let's take these points, we'll plug it in, and we'll see what numbers we get out. Negative 4 plus 1 is negative 3. Negative 3 squared is 9. 1 minus 4 ninths, that's some positive number. That's primarily what I'm interested in, which shows that the function's increasing before negative 3. It has positive slopes. It's going upwards. So it's increasing. Plug in negative 2. Negative 2 plus 1 makes negative 1. Negative 1 squared is 1. 4 over 1 is 4, and 1 minus 4 is negative 3. I don't care that it's negative 3. I'm just interested in the fact that it's negative, because that shows that the function is decreasing in this interval where that little test point is. If you plug in 0, you get 1 over 4 minus 1. That's also negative. So that shows that these number lines don't always just flip-flop, increasing, decreasing, increasing, decreasing. Sometimes they stay the same. Then lastly, f of 2, we get 2 plus 1 is 3, 3 squared is 9, 4 ninths, and then 1 minus 4 ninths is a positive number, and so we would be increasing. So increasing, decreasing, decreasing, increasing. All right, so now we're ready to state our final answer. Right here, where it seems that it's changing from increasing to decreasing, looks like we would have a relative maximum, and in fact we do. Relative max, because the function's going up and then it's going down while it's continuous at negative 3. The asymptote wasn't there. And right here at this critical point we have a relative minimum, because the graph goes from decreasing to increasing. So it's the low point on a graph. Now here at negative 1 it goes from decreasing to decreasing again, but this is important. I know it doesn't happen in this example, but even if it did go decreasing to increasing, this would still not have been a relative minimum, because there was an asymptote there. This was not a true critical point. So you have to be real careful reading these number lines. It's very easy to slip up and see if it's increasing to decreasing or vice versa and call it a relative max and min when it's really not a relative max and min. So this is how we go through and find relative extrema. Okay, so here's a graph of the function x minus 4x over x plus 1, and sure enough, in hindsight, these answers make perfectly good sense, because right here at 1 it seems to be a relative minimum. It's the local minimum. It's the lowest point around. And there is a relative maximum back here at negative 1 to negative 3 right here. It's the local maximum. And right here at negative 1, I see that vertical asymptote. And sure enough, it was decreasing before and decreasing after the asymptote. So even if it had been increasing to decreasing, there wouldn't have been a maximum up here simply because of the asymptote that we could have easily gotten wrong, misreading the number line that we have.